Good evening, children. In previous session, I taught the relationship between change in enthalpy, change in internal energy, and its relation with the P delta V. That is product of pressure and change in volume. Right. This is part of the chapter Thermodynamics. Thermodynamics. In this, the important expression, that is delta H, is equal to delta U plus P delta V. This I taught in previous class, where delta H, delta U, delta V stands for change in enthalpy, change in internal energy, and change in the volume occupied by the system. Right. This is one of the important expressions in thermodynamics. And here you have four variables. 1, 2, 3, 4. Out of these four variables, if any three variables are known to us, the fourth unknown variable can be calculated. That way it can be used. Means this formula can be used in numericals. Now let us see the other expression. That is P delta V expression we are going to see. Means in its place, that is in place of P delta V, we can substitute something. When is this possible and how to get that equivalent part of P delta V? Consider there are two reactants, right? Volume occupied by one reactant is, say, A. So VA is volume of reactant A. So PVA is equal to nRT. Here N stands for quantity of that system. That system is A, so we can write A. Let this equation be 2. Now imagine another system or another reactant. There are two reactants or there are two systems reacting chemically with each other. In the case of second system, we can write PVB is equal to NBRT. And here B is second reactant. Right. B is second reactant. This is for first reactant, this is for second reactant. In this expression, P stands for pressure exerted by the system. VA stands for volume occupied by the reactant A of the system A. NA stands for quantity of the reactant A. R is known to as universal gas constant. Capital T stands for absolute temperature. In the case of second reactant of the system, this is the expression. Now, P, what I am going to do is, just I will give a different look to this equation. Right? PVB minus VA. Right? This expression, let me write first completely and then I will make it short. PVB minus PVA is equal to NBRT minus NART. Right? Here in this part, LHS, P is common, so we write PVB minus VA is equal to RT is common in this expression. So what I am going to do is NB minus NA I will write multiplied by RT. Right. Now pressure I will write as it is P. And VB minus VA means change in volume. So I will write change in volume as delta V. P delta V. Right? Here delta V is equal to VB minus VA, that is delta V. Right? This is equal to now Mg minus Na, number of moles of the reactant B minus number of moles of the reactant A. Right? Now this is equal to delta Mg, right, into RT. This is expression number 4. Right? Now we can substitute fourth expression in expression number 1. So when expression or equation number 4 is substituted, when equation 4 is substituted in equation number 1, we get delta H is equal to delta U plus P delta V is there, and P delta V is equal to delta MGRT. So I will write plus delta MGRT. This is expression number 5, and this is important expression in thermodynamics. Equation number 1 and equation number 5. 1 and 5 expressions are very helpful in working out the numericals. Now look at this expression. In this we have 1, 2, 3, 4, 5. 5 out of 5 variables, R value is known to us. It's a constant. Right? So except that R, we have 4 variables. Out of these 4 variables, if we know any 3 variables, we can calculate 1, 2, 3, 4. Out of these 4 variables, if we know any 3 variables, the 4th unknown variable can be calculated. That is advantage of this equation. And here delta Mg stands for difference in number of moles of the substances, and they must be in gaseous form. Imagine if an hypothetical equation of this type is there. A has given rise to B. Imagine. This is one hypothetical, imaginary equation. Right? And these are in gaseous form. They must be in gaseous form. Then number of moles of products minus number of moles of reactants is equal to delta Mg. In that way it is. So delta Mg stands for number of moles of products minus number of moles of reactants. Right? So that's about the important expression which is useful in thermodynamics. Now we'll move to sign conventions. The other important part of this chapter, that is sign conventions. Now heat energy, that is symbolically represented by the letter Q. Right? When a system is undergoing a change by absorbing heat energy or by releasing heat energy. Absorbing means system can absorb take energy from the surrounding, or that system can give energy to the surrounding. It can happen in any way, right? So in that case, if Q is equal to positive, then it shows energy is taken from the surrounding. Energy is absorbed from the surrounding. Next, if Q is negative, then it implies that energy is transferred from system to the surrounding. So Q is equal to negative. So this shows energy is transferred from system to surrounding. Right? This is about heat energy, sign convention in heat energy. Now let us see sign convention in the case of enthalpy. Right? If enthalpy value is positive, means that system during its change, right, it is absorbing energy, means it is endothermic reaction. Endo means taking in, right? So shows that it is endothermic reaction. If enthalpy value is negative, then it shows exothermic nature. Of the reaction. That's about sign convention. Okay, children, now let us see important properties of the system. We have mainly two important properties. They are extensive property and intensive property. These are the two important properties. So first property is extensive property. Extensive property. Now what is meant by extensive property and what is its significance? Let us see. There are some properties which depend on the total quantity of the matter present in the system, or they may not depend on the quantity of the matter present in the system. Right? Quantity of matter, that refers to the amount of substance present in the system. Right? So that way we have two properties. One is extensive property and the other one is intensive property. Now let us see what is meant by extensive property first. That property which depends on, as I told you, two properties are there, right? that property which depends on the total quantity of the matter in the system is called extensive property, right? So this property depends on the quantity of matter present in the system. Now let us see example for this. Is mass. Volume, right? Mass of the system. In a particular system, if the quantity of matter is more, its mass will be more. In that way, volume of the system. Volume occupied by any system is more. Space occupied by any system is more. Then its volume is said to be more. Right? So that's about extensive property. Now we will be moving to intensive property. This is second type. Intensive property. What is meant by intensive property? This is quite opposite to extensive property. In the case of intensive property, the total quantity of matter present in it. This property, see, earlier one depends on the total quantity of matter present in the system, whereas this property does not depend on the total quantity of matter present in it. So we can write does not depend on the quantity of matter present in the system. Now let us see example for this. Density is intensive property. How can we say that density is intensive property? Here, if you take small ice piece and throw into a tub containing water, then that small piece of ice begins to flow on the surface of water. See, mass of that small piece of ice is 10 grams. Now, I will take 500 grams of ice cube and I will throw into tub. 500 grams of ice cube is much bigger in size. Its weight is also more than 10 grams of ice. So it should sink, but it will not sink. It floats on the surface of water in that tub. Third case. First I took 10 grams, next 500 grams. Now 1 kg ice cube I will take and I will throw into water of that tub. Then that 1 kg ice cube will not sink. It floats on the surface of water. Means here the thing is, when we move 10 grams to 500 grams, 500 grams to 1 kg or 1000 grams of ice, then what happens is, no doubt, mass of ice increases, but density of the ice, it is remaining same, right? So density is mass per volume. Since density is remaining same, even though the quantity of matter, that is in solid form H2O molecules, are increasing, but here the main thing, this was taught in previous chapter. Ice has cage structure, means empty spaces or more. In chemistry, cage, CAGE means unoccupied space, empty space or void, VOID. Because of this reason, what happens is, in the formula D is equal to M by V, V becomes more and more. Right? Therefore, density of ice doesn't increase. So, here quantity of ice, quantity of matter or ice of the system is increasing, but density is not increasing. That is the reason why it flows. So here, intensive property is not at all depending on the quantity of the matter. Next is temperature. Temperature. This is also intensive property. Let me give one example. Class 12th student age is around 17 years. Newly born baby's body temperature, if we measure, right, with the help of digital thermometer, it shows 37 degrees centigrade. Newly born baby temperature. Weight of that baby is around 3 kg, not more than that. Okay. Very healthy baby means very rarely it is 4 kg, 4.5 kg, up to that. Fine. Here, newly formed baby weight, you compare with 17 years student's weight. Class 12 student age is around 17 years. Right? 0-year baby to 17 years student. Body temperature. If their bodies are not febrile, then their body temperature will be 37 degrees centigrade. Here sizes of bodies are different. Newly born baby size, 17 years student size. Right? Next, if we move to athlete of say 35 years, a good player, his age is say around 35 years. Right? Here 0-year baby, 17 years class 12 student, 35 years athlete. Their bodies are not febrile. Now, the temperature of bodies of these persons, if they are measured with the help of digital thermometer, then it shows 37 degrees centigrade. Sizes of bodies are different. All 3 bodies sizes are different. Right? Newly born baby size is very small when compared to 17 years. Student of class 12. Again, 17 years student of class 12 when compared with 35 years athlete. Again, there is a lot of difference in the weight. So here the point is, even though the weight of the bodies, total weight of the bodies are increasing, but temperature of those bodies are remaining constant. So, temperature is intensive property. Even though the sizes of the bodies of the persons are increasing, temperature is remaining constant. Okay. Now we will move to pressure. Right? If we sit in a very small room, say bathroom, we are sitting. Right? In that bathroom, air is there. That air is exerting pressure on our body, on the head, on the shoulder, on the nose, right? On the ear. That air is exerting pressure. The pressure exerted by the air in the small room, say bathroom or kitchen room, is 1 atm, 1 atmosphere. Next, if the same person, imagine, is sitting in classroom. Classroom is bigger than the kitchen room or the bathroom. In classroom also air is there. Right? Size of the classroom is much bigger than the kitchen room. So quantity of air should be more in the classroom. Right? But the pressure exerted by the air is equal to 1 atmosphere only. Next, if the same person, and that person be student, enters into the ground. Ground is much bigger than classroom. So quantity of air should be more, pressure should be more. But what is observed practically is, even though the ground is much bigger, containing huge amount of air, pressure exerted by that air is equal to 1 atm only. This is the point. So irrespective of the pressure, right? Irrespective of the air, in bathroom particular amount of air, classroom more amount of air, ground still it has more amount of air, right? So here quantities of air increasing from bathroom to classroom, classroom to ground, but the pressure exerted by that air is remaining constant. That is equal to 1 atm pressure, right? So here density, temperature and pressure are intensive properties. These three are called intensive properties. If the property depends on the quantity of the matter, extensive. If it doesn't depend on the quantity of that matter, then it is intensive property. Okay, so that's about extensive and intensive property. This comes under thermodynamics only. This is continuation of thermodynamics. Now we'll move to enthalpy changes associated with the reactions. Means there are some reactions wherein enthalpy change is associated with that. Next, if these enthalpy changes are measured in standard conditions, they are said to be standard enthalpy of the reaction. Right? Now the topic is measurement of change in enthalpy in this we have standard enthalpy of the reaction. First one, standard enthalpy of the reaction. Standard enthalpy of the reaction. Now in this standard enthalpy of the reaction, what does standard mean? Let us see. Standard means known. What are known? Temperature and pressure. These two are known. When change in enthalpy is associated with a particular reaction at 298 Kelvin temperature and at 1 bar pressure. These are standard conditions. Standard means known. What are known? Temperature is known, that is equal to 298 Kelvin. Pressure is also known, that is equal to 1 bar. This is according to IUPAC norms. Right? Bar is slightly bigger unit than atmosphere. Atmosphere is unit of pressure. Bar is also unit of pressure. Right? And here, standard enthalpy of the reaction means change in enthalpy associated with the reaction. Change in enthalpy means, again here, it can be plus or minus. If change in enthalpy is minus, then it is exothermic reaction. If change in enthalpy is plus, then it is endothermic reaction. So, change in enthalpy associated with a reaction at 298 Kelvin and 1 bar pressure is said to be standard enthalpy of the reaction. And this is symbolically represented like this: delta H naught. Here superscript, the 0 indicates standard, which means known. So temperature and pressure are known. So it can be defined or written like this: change in enthalpy associated with a reaction at 298 Kelvin temperature and 1 bar pressure is called standard enthalpy of the reaction. Right, in this we have different types. Now let us see two types in this category. First type is standard, I am abbreviating it as STD, standard enthalpy of fusion. This is first type of what they call standard enthalpy of the reaction. This is first type, standard enthalpy of fusion. Fusion means it is nothing but transfer of a system from one physical state to the other physical state. Means solid to liquid. Imagine when 1 mole of a solid substance is converted into liquid substance in standard conditions, then it is said to be standard enthalpy of fusion. So, in this case, 1 mole of a solid substance is converted into liquid in standard conditions. Standard conditions means it is referring to particular temperature 298 Kelvin and standard enthalpy of fusion. Now let us see one specific example for this. And here we require solid substance and its quantity should be 1 mole. Example, H2O. H2O is in solid form, means it is ice. Now we need to give particular amount of energy to this solid substance so that it can become liquid substance. Right? Quantity of that solid system should be 18 grams. Right? It is converted into liquid. And in this case, standard enthalpy of fusion, it is symbolically represented by delta H fuse or delta fuse H. FUS stands for fusion. This is equal to plus 6 kilojoules per mole. Why should we write here 0.00? You recall significant figures. If SF value, significant figure value of any number is more, means it is associated with more and more accuracy. Right? So that is the reason. Fine. That's about standard enthalpy of fusion. Here standard, so superscript 0 should be there. Now we will move to the second type, that is standard enthalpy of vaporization. Standard enthalpy of vaporization. And it is symbolically represented by delta wave H naught. Delta wave. Wave means vaporization, like fuse means fusion. So delta wave H naught. This is the symbol. Now how should this be defined? Standard means again known temperature and pressure values which are known to us. The standard enthalpy of vaporization means change in enthalpy associated with a reaction wherein 1 mole of a liquid substance is converted into gas. In some reference books, it is written standard molar enthalpy of vaporization because we are taking 1 mole of liquid substance. So also this title, standard enthalpy of fusion. In some textbooks, it is written standard molar enthalpy of fusion because here also we are taking 1 mole of the solid substance. So according to the concept, change in enthalpy associated with the system. System means reactant or reactants. With the system or change in enthalpy associated with the reaction. We can write reaction also. Let it be reaction wherein 1 mole of a system, here let it be system, a system in liquid form is converted to gaseous form in standard conditions. Right? In standard conditions. Now let us see best example. Again, standard enthalpy of fusion. This standard enthalpy of fusion refers to conversion of 1 mole of solid into liquid in standard condition. And standard enthalpy of vaporization. Here 1 mole of liquid is converted to gaseous form. Okay, now let us see example for this. H2O, this is liquid, so we write L in brackets. Right? It is converted into gas. Quantity of this liquid is 1 mole. And in this case, delta wave wave means vaporization. Standard enthalpy of vaporization, delta wave H naught, is equal to, here to convert liquid into gas, we need to give energy, means it is endothermic. So plus only. So plus 40.6 kilojoules per mole. In some books 40.79 is written. Yeah. So that's about the standard enthalpy of vaporization. Now we will move to third type, that is standard enthalpy of sublimation. Standard enthalpy of sublimation. Right. Sublimation means a reaction wherein a solid substance is directly converted to gaseous substance. Means its physical state should be changed directly from solid to gaseous form. In between, liquid state should not be there. Right? So standard enthalpy of sublimation. It is symbolically represented by delta sub H naught. Right. Now, let us see standard enthalpy of sublimation. How should this be defined? Change in enthalpy associated with a reaction wherein 1 mole of a solid substance is directly converted to gaseous substance. Once again, change in enthalpy associated with a reaction wherein 1 mole of a solid substance or solid system, we can say, is directly converted to gaseous form in standard conditions. In each concept we have to add that in standard conditions. If we do not want to add in standard conditions, we can write at 298 Kelvin temperature and 1 atm pressure. So concept is like this: change in enthalpy associated with the reaction where in 1 mole of a solid system is converted to gaseous form directly is known as standard enthalpy of sublimation. And here we have specific example for standard enthalpy of sublimation, right, as in the other cases. Now what is that example? Specific example in this case, let us see. Here we have carbon dioxide, solid carbon dioxide, dry ice. If we give small amount of energy, directly enters into gaseous form. So solid CO2 will become gaseous CO2. Number 2, example 2, camphor we can take, or we can take naphthalene balls, right? Naphthalene is solid. If we heat, directly it enters into solid form. And here, when it enters into solid form, 73 kilojoules amount of energy is taken by solid naphthalene, whose quantity is equal to 1 mole, right? So, example, naphthalene. So this is in solid form, right? And when this is heated, directly it enters into gaseous form. And standard enthalpy of sublimation is symbolically represented by delta sub H naught, and this is equal to 73 kilojoules per mole. Means here we need to take 1 mole of naphthalene, right? Then it enters into gaseous form when energy is given, and that energy is equal to 73 kilojoules. Now let us see standard enthalpy of formation. It is symbolically represented by delta F H naught. If we write fuse, F-U-S, it is fusion. If we write F, it means formation. And the superscript indicates standard. In chemistry, standard means known. Temperature is fixed, it is known. Pressure is also fixed according to IUPAC norms. So that is also known. Now, concept, let us see. Standard enthalpy of formation means change in enthalpy associated with a reaction wherein 1 mole of a substance or system is formed from its respective elements in standard state. This is the definition. Now let us see the elements. Those in an example, we can take water. 1 mole of water is formed from its respective constituent elements. Those constituent elements are H2 and O2. When these chemically combine, it gives rise to 1 mole of H2O. So according to the definition, 1 mole of H2O is formed in standard condition, that is at 298 Kelvin and 1 bar pressure. Now in this reaction, delta F H0 is equal to 285.8. You can round up to 286 kilojoules per mole. Here in between, hydrogen and oxygen bonds should be formed. Whenever bonds are formed, energy is released. So enthalpy value should be associated with negative sign. So we can write here minus 286 kilojoules per mole amount of energy is released. So here quantity of H2O formed is equal to 1 mole and its respective constituent elements are hydrogen and oxygen. So that's about standard enthalpy of formation. Now I am holding with this topic, and in next class we will see the other types of enthalpies of formation. Thank you, children.